Yeah, just my notes for you.
I'm done.
Okay. So, before we start, a couple of administrative announcements. You probably have all got your graded homework 1 back by now. You probably have all seen the sketch forum. The numbers are, given the amount of complaints I heard, the numbers are surprisingly high. It either means you did a lot better than you expected, or it means I was a lot more lenient of a grade than you expected. Whichever way it is. The average was, I think, 43 out of 50. The median was something insane like 47 out of 50. So, well done. Bit of all that. I will be posting a solution set shortly, just so you can take a look at what kinds of things I expect to see, and that will help you sort of get a gauge for why you got points cut if you did. And if you do have questions, feel free to post in the forum. I mean, in the submission comments to your homework. The reason to do that is just makes it easier for us to keep track of all the comments that are flying around, so we don't miss anything. It also keeps a nice log of all the comments, so it's helpful to us. You have a week. If you decide a week from yesterday, when we posted so yesterday 5 p.m. that you wish to change something, we will not look at it. We have to move on to the next assignment, which will be coming soon. So you have at most a week to sort of ask questions about your thing. Okay, so don't waste any time. Preferably do it soon. Apart from that, the next thing I want to mention is the project. You probably have also noticed that I posted a deadline for submitting your initial project proposal. Now, the project proposal consists of essentially 2 lines of text, so it's not a lot of work. It's the name of the paper you want to present, along with its full citation and the number of citations it has received based on Google Scholar, and a link to the actual paper. Okay, and this might be the actual source, or if it's behind a firewall, a PDF, something that I can actually click and read. Not click and have to log into 10,000 different locations and hope that I can read. Okay. So it's not much I'm asking. So I expect that you will do exactly that. 1 second. I have asked that people form groups of 2 or less. I would strongly recommend forming groups of 2. Of course, because of parity issues, there might be someone left out, but to what extent possible, make it groups of 2. I can't quite check this, so please let me know if you're having trouble. I think what I've set up are explicit project groups, that if you go into Canvas, go into the people section and look for a group called project groups, you should be able to drag yourself or put yourself into a group along with a partner. And each group, there'll be a whole bunch of groups. I think I've created 40 of them so far, and I can create more, that will have at most 2 people in them. So if you work with a partner and you say, okay, we want to go join a group, take whatever group number happens to be available, and just put your names in, it should work. If it does not work, let wait till next Tuesday at 4:59 p.m. to let me know. Okay, you've got a week to figure this out. So just try it out today and see if it works. You have a week to sort of think about what kind of paper you want. If you read the project guidelines page, there's a fair amount of detail there. I'll give you an example of what I want as the output. Like I said, it should be a paper from an Algorithms conference. A lot of these papers often appear in journals later, and that's fine too. In fact, the paper I linked is a journal paper that is one of these Algorithms venues. The reason I say that is not because I require you only to do that. It's because if you're not familiar with algorithms in general, this is a helpful way to navigate your way into what I would consider a reasonable paper. Pretty much any paper from those venues I would consider reasonable. If you really want to look at a paper that isn't in one of these venues, I am definitely open to the idea, but you're going to have to convince me. And so that is just a rubric for you to work with. Say, okay, papers that look like this. A lot of people will find, oh, I have this paper networking that had a theorem somewhere. That may or may not work as a paper for this class, and it depends. And so we'll have to talk about that. Okay, questions. First there was a question back there.
Yeah, do we have to have the groups figured out before the time of the proposal?
Yes, because you have to submit your proposal. All proposal activities will be submitted as a group. The submissions are as a group. Just saves effort. Otherwise, you're all submitting different things, you're going to match them up. So preferably if you can get your groups organized by that time. Yes.
Can we change papers after this? Like if we look at citations or something and say we want to do that paper instead?
What do you mean change? You mean submit your thing next week and then change your mind?
Yeah.
I would prefer you didn't. You'd have to have a really good reason for shifting. And your reason would be what? You like this one better?
Yeah.
I would view that on a case-by-case basis, and I would give you only a few days to make the change. It should, like I said, that you don't. It doesn't have to be the perfect paper. It has to be the best way I have found to do this is to start with your own interests. Don't. If you start going and say, "Wait, I'm going to go look at the last 10 years of papers in this conference," you're just done. There's too much to learn. There's too many things, and either you'll find everything too interesting, or you'll find nothing interesting. You'll just either way, it's not going to help you. Start with your interests. You have an interest in, say, I don't know, machine learning. Say, so you say, okay, I'm interested in machine learning. What kind of interesting theory areas in machine learning can I explore? Or maybe there's something to do with pack learning. Or maybe I will look at some. So there's a way to navigate quickly, right? You only need one. You don't need to find the best paper. I mean, I suspect that any paper you find is not going to significantly advantage or disadvantage you. And if I do think it's going to be really hard, I will warn you. So when you submit your proposal, I will be looking over all your choices. And this is very common. If I think that your paper is either you've bitten off too much or it's too, not the right thing, I will get back to you and I will give you a suggestion. I will say, look, you want to do this topic, you've chosen this paper, I think you should do this other paper instead. And there will be some back and forth there. So I'll help you come up with the right paper. The goal, which doesn't mean you should just come up with any old thing and wait for me to suggest it. You should do about 95% of the work yourself. But if you start with your own interests and work from there, it'll be a lot easier than trying to look at a gigantic body of papers and figure out something that might be interesting. It'll be too overwhelming for you. So find a partner, talk to them, figure out what might be interesting, and then go from there. And then, I'm happy to take questions from people. I'm interested in this topic. Do you think there's something there? Again, up to a point. I can't take questions from every single person with that thing. But if you do your homework and say, okay, I'm interested in this. I found these 3 papers. What do you think? I'm willing to handle a couple of those requests before the deadline. It's not, it's a conversation we can have. It's not something I'm not testing you on your ability to choose a paper. I just want to choose something. There's a small amount of points associated with submitting some time. It's not a lot, but there's enough to sort of give you a little bit of incentive to make sure you submit on time. And all the usual other policies apply. But when you have a few points, you lose some fraction of those points not being a part. Yes?
Are these conferences open to the public, or do we need to log?
They usually are, and the thing with computer science, especially in algorithms, is that people tend to ignore issues of copyright. So in other words, if you find a paper title that you think is intriguing, or you maybe find the abstract because it's on, and the rest of it is paywall, if you Google the title and the authors, you will almost certainly find the paper. Almost certainly. I'd be very shocked if you couldn't find the paper, especially if it's, say, more than 3 years old. Yeah, and less than 20 years old. So one thing I did say that I don't want papers before 1980. I would almost want to amend that to papers before 1990, just so that you want to be a little bit more current. But again, I'm flexible. These are not hard and fast rules. The 80 rule is hard and fast. The 90 rule is not so hard and fast. But I would strongly recommend looking at things that are more recent, right? Especially given the kind of things we're studying in class. You will find that a lot of the stuff that is covered from the 90s onwards will be very familiar to you after, given what we're talking in class nowadays in the last few lectures. Any other questions about any of this? It's due next Tuesday, 5 p.m. It's an online text box thing. You just have to put in, like I said, 2 lines of text, name the full citation of the paper, and the number of citations that Google Scholar found for it. If you ever use Google Scholar, you'll know that. If you look at the paper title, it'll say so-and-so paper, so many citations. You don't need to do much else. The numbers are not entirely reliable, but they give me a sense. I just want to make sure you don't pick a paper that has 3 citations. And an actual link to the paper. Okay. If you're having trouble finding the paper, again, but you worked very hard and you've done a bunch of your homework, and it's something that would take me more than 2 minutes to figure out myself, then I'm willing to help. If I go look for the paper, it takes me 2 minutes, I'm going to say, go look. Okay. All right. Any other questions before we move on? Yes?
So is there any condition on the length of the paper?
No. Most of the papers you will find in conferences have a fixed length because conference formats require a paper to be 10 pages or less.
Okay.
That just means that the papers tend to be very abbreviated. It is in your best interest to find a version that's longer. So if you've heard of the archive, a lot of these papers, especially in the last 10 years, I would say any paper you find in a conference is probably also has a longer version of the archive. You can link to either version you want. The conference referencing tells me that this is a paper that's been peer reviewed, it's been respected, it's a good paper. The archive link tells me here's the paper you're going to read. And so the length of the paper is an issue. These are hard papers anyway, even if they're 5 or 6 pages long, they're going to take a while to understand. So I'm not particularly worried about that. You know what I mean? One last comment is, the point of doing the project is to understand the paper. So by definition, it is unlikely that you will understand everything in the paper when you start trying to skim it. Which is why I said, go with your interests, go with the introduction, read the abstract, try to get a vague sense of what the paper is about. And that should be enough to do a pattern match. Like I said, these papers are all, if you look for papers in algorithms conferences, they're all going to be at a reasonable level of difficulty. So you're not going to be, you're not worried about, oh my god, I chose a really hard paper by accident. That's my job to make sure I don't think it's too hard for you. And I've done this in the past. Told people, no, don't do that too. So you shouldn't expect to really understand the paper very well. You should expect to be able to understand the title and what problem they're thinking of looking at, and some very vague sense of what the context is. And I'll spend more time talking about how to write your report, how to think about writing your report, and how you should read the paper once we finish with this. Okay. All right. Okay. So much for that. Let's move on. So I want to quickly wrap up something from last time. So if you recall, we were talking about this problem of maintaining frequent items. And we talked about the simple version of the problem where I said, I promise you there's an item that has a frequency that's more than, it has more than half the total frequency, total number size of the set. In other words, it occurs more than half the number of times in the total set, and I want to find it. And the algorithm I gave was this very simple algorithm, which basically uses 2 units of storage, one counter and one label storing items, that keeps track of this, and this was basically the algorithm. You look at the first item, you see if it's, you take the second item, if it's the same thing, then this could be a possible candidate for being the majority element, so you keep track of it and keep its count. And so you just keep track of this one item. And if you start seeing enough items that this count of this subtracts down to 0, then you know, okay, this initial prefix does not have a majority item. I'm going to get rid of it. And so you throw it away and you start all over again. And that's what this algorithm does for you. And the crux is that you can show that the frequency reported for this item that you report at the end is some number. It's obviously less than the true frequency because all you're doing is subtracting. You never manufacture counts. So it's less than the true frequency, but it's more than something. It's more than the true frequency minus all the possible times you could subtract something from it. Right? If this is the frequency of the item, every other item could cause a subtraction from its count, which is n minus fi. So its true frequency is the true frequency is fi. The subtractions could be n minus fi, and therefore the reported frequency will be fi minus all of that. But since we're guaranteed that if fi is the maximum item, fi is more than n over 2, we know that this will end up with a frequency of at least 1. And since you only have one storage, this is the one you're going to report in your time. Okay? Again, this is one of these little puzzle tricks you get in sort of interview questions because it's so cute. But it's also an important point here that you're essentially approximating the true frequency by something else, but that something else is reasonably close. It's not reasonably close really, but for the purpose of this problem, reasonably close means it's more than 0. Because that's all we want to find. And now you could say, well, that's no good. I mean, I don't want to just find an element that's a majority. I want to be able to do something a bit more general. I want to find these top items that you promised me I could find. And in fact, you can generalize this idea. So if you choose k slots instead of one slot, but do the same thing. So now I had one slot in a count. Imagine I have k slots and counts for each. So the first item comes in, I put in one slot and increment the count. Second item comes in, there's an empty slot, I put it in. So I quickly fill up k slots, right, with k items, maybe with some incremented counts for different if I have k slots. Now the next item comes, and there's nowhere to put it, right? So I have to decide what to do. And so the trick is now you subtract one count from each of the buckets. So you have your buckets now. Each bucket has an item and a count, item, count, and the k of them. You subtract one count from each of those. Okay. Maybe nothing happens. They're still full. In which case you throw away this item and keep going. Maybe one of those items goes to 0. You throw that out, put this one in with a count of 1 and repeat. So it's like a generalization of the case with 2, with one item and a counter, but for k. And it turns out that using essentially the same reasoning, or a variant of the same reasoning as you did before, you can now argue that the difference between the estimated count of an item to report and the true count is not n over 2, as before, it's n over k. So the error has become smaller. Okay. Right? So as k gets larger, the estimate of the true to the small frequency gets smaller. And for example, if you put k equal to 100, the error estimate is 0.01 times n. So now what does this mean? This means that essentially, think of items that have a frequency of more than n over k. So before we thought of an item of frequency more than n over 2, it was a majority item. Now think of an item that's frequency more than n over 100. Okay, let's say it's n over 100 plus 5. What does this guarantee tell us? This guarantee says that in the final answer, this item must be recorded with a frequency of at least 5. Because the difference between it and its true frequency is at most n over k. And I just said its actual frequency n over k plus 5. But if it's going to be reported with a frequency of at least 5, it's going to be reported in particular. Which means that I will see it. Which means that I've caught this item with just 100 units of storage, or 5 units of storage. I've caught this item, well, not 5, sorry, whatever k units of storage, I've caught this item. So with k units of storage, I can guarantee to capture an item that occurs at least n over k times. Okay. That's the idea here. Just like with 2 units of storage, you capture at least. So this idea of approximating the true count allows us to reduce the size needed to keep track of the items while still maintaining some approximation to the items we are looking for, the high frequency items. Again, this kind of trick is used over and over again when you're doing any kind of large data frequency count estimation, sort of keeping track of most popular items, so on. Yes?
So at the end of the algorithm, would we know the k most frequent items in the string?
No. You will have k items, each of which has a frequency of somewhere between n over k and n over k plus minus whatever your error is. Right? You have the true frequency plus n over k. That's not the k most frequent items. Because what could happen is, one of those items that's in the top list might go down. One of them might not get subtracted as much, and there'll be some variant. But what you're guaranteeing is that every item you do produce has at least a certain frequency. So they're all popular, they may not be the most popular. So that's a subtle difference. But they're all at least a certain amount popular. Okay? Because the problem is that the k most frequent items, it could be that there are 2 items that are very frequent, then everything else drops off to some very small frequency, but they are the most k frequent items. I'm not guaranteeing any properties for that here. I'm only saying if you do have lots of frequency, we'll find it. Okay. It's the same thing with similar in spirit to what we said the median, that I can't approximate the value of the median, but I can approximate the rank of the median. Similarly here, I can approximate items who have large count because they have large count. I can't guarantee to get the kth most frequent item because that count could be very small. So this distinction is important. In fact, it's actually hard to find the kth most frequent item. That's another story. You can prove that. So just to review, if you want to get frequencies, there's an exact algorithm we know it'll take omega n space because you've got to keep track of all the frequencies. If you want some n over k approximation additive, it'll require O of k space. If you think of k as 1 over epsilon, this is a number this is a way of thinking you should start getting used to. Epsilon being some tiny number, so 1 over epsilon is some hopefully not too large number. You can get an epsilon n additive approximation using 1 over epsilon space. And again, the point is this is constant space, or constant number of words of space. You don't need space even square root n or log n. It's effectively a constant number of words of space gives you this error. And that's a very strong result. Right? It's saying that the amount of storage I need relates only to the error I'm willing to pay and not to the actual size of the input at all. Which is a little strange and cool. And that's why these things become very useful for large data problems. That they've decoupled they've separated out the error issue and the size issue. Size issue is gone, it's just the error issue. Okay. A minor point is that an epsilon n additive approximation is a 1 plus constant times epsilon relative approximation as long as your frequencies are large, right? If your frequency is 5, if your frequency is n over 5, and you have an epsilon n additive error, then your approximation is going to be n over 5 plus epsilon n. Let me write this out here. So let's see. So let's say your frequency is, the true frequency is f is equal to n over 5. And your approximated frequency minus f is less than or equal to epsilon n, then your f hat is going to be greater than or equal to n over 5 minus epsilon n, which is equal to n times 1 over 5 minus, oh sorry, n over 5 times times 1 minus 5 epsilon, which is now a relative error approximation. You may not be able to see this, let me move this up a bit. Yeah, n over 5 minus, so this basically is now, you have the true frequency times a relative error approximation, which is a O of epsilon. This doesn't work, of course, if f is very small, right? If f is like 10, and you're saying I have an epsilon and additive error, that could be very bad. So that's why these kind of things approximate large values, not small values, if you're willing to, if you pay attention. Okay? All right. So that's all I wanted to say about the basic idea of frequency approximation. And are there any questions, Frank? Yes?
So would you have to use the deterministic algorithm in order to figure out, or in order to handle a good case for small n?
There are separate things you can do. So generally speaking, dealing with small frequencies is hard. There's just no easy way because there could be so many of them, and it's so hard to keep track of them. There's not too many things you can do, but there are specific cases where you can do certain things, and it gets a little bit more. Maybe there's a project paper they're waiting to be looked at. There are a bunch of papers on this topic. Okay, so let's move on to another topic. What I'm going to talk about today, and this is sort of inspired by a discussion I had in office hours, so I want to thank those who came. You know who you are. So this is why it's good to come to office hours. So we've been talking about, so far in the class, at least till last lecture, we were talking about deterministic versus randomized algorithms. If you think of this kind of square box, what you learn in your undergrad algorithms class, or your first algorithms class, is everything in that first box up there. It's deterministic algorithms that run correctly, always give you the correct answer, right? The basic sort of stuff. And the first thing we do is say, well, suppose we allow ourselves some uncertainty in our calculations, uncertainty in our correctness, we get to randomization, right? And we've seen examples. So for example, someone give me an example of a deterministic exact algorithm that you might come across in an undergrad algorithms class. Anything you want.
Prim's algorithm.
Sorry?
Prim's algorithm.
Prim's algorithm, so MST, right? So minimum spanning tree. And we'll put prim. Okay? So what's an example of a randomized algorithm we've come across so far in this class? Anything you want. Pick one. Surely you remember one of the things we've covered. Please tell me you remember one of them. Anyone? Sorry? But a specific, for a problem, can you name something you solve for a particular problem?
Like a min cut, we use min cut.
Very good, min cut. And this is good because min cut also has deterministic algorithms, which are exact, and we'll see those later, but we're going to look at min cut here. Okay? Okay? It gives you the answer, but there's a certain probability of being wrong. Okay. We've also seen now, if the lecture from last week and the next few lectures, we're going in the horizontal direction. We're going away from exactness to approximation. So we're losing precision in our answers. And we've seen algorithms today, for example, this one about computing high frequency items. Right? It's a deterministic but approximate algorithm. Right? And of course, we will, as we go forward, see places where we apply both of these things at the same time. We get uncertainty in the computation and we get errors in the answer. And we've seen examples of this already. In fact, what would be an example that appears in this section here? You've already seen an example of this. Anyone?
Bloom filters.
Sorry?
Bloom filters.
Bloom filters I would consider just here. Because they're randomized, but there's no number you're trying to approximate, right? It's a membership question, it's a binary question. Is it there or not?
They give you an approximate.
Sorry?
They give you approximates for the membership, kind of.
Right, but they give you an uncertainty whether the item is in the set or not. It's a binary thing, which I don't consider technically an approximation. Really. It's a 0 or a 1 in some sense. But we've seen some in class. We saw it last week.
Finding the median.
Approximate rank finding, right? So we talked about approximate rank finding, approximate median finding, I guess. Because there the algorithm was randomized. We were doing sampling, and we were getting a rank that was an approximation of the true rank, right? So you will find as you go along, even as you read your papers, that you will see things that could be, and then by the way, there are other dimensions to this as well. But at least for now, the two dimensions of of relaxing the notion of an algorithm, like go to randomization and approximation, you will see all kinds of examples of this, right? And they're drew them this way because they are independent of each other. One, you don't necessarily need one to have the other, but they tend to work very harmoniously together, which is why all of your large data problems end up in this space here, right, for the most part. But of course, you want to understand these two dimensions separately so we can see how they get put together, which is why I was talking about this side, and now I'm talking about that side. Okay. And so the way to think about approximations fundamentally, and I said this last time, is that it's a trade-off. It's a trade-off between precision and usage of the resource. The resource could be time or space or whatever. But this is the trade-off you're paying. You want to use as little of the resource as you can, and you're willing to pay some error in terms of your precision. Okay, so that's the fundamental choice you have to make. And historically, the study of approximations did not come from dealing with large data problems. It came from studying hard problems to solve, well, NP-hard problems. So the classic, if you think of classic approximations, like maybe in the 80s when people first started thinking about this, right? You'd have a problem that was NP-hard, and we know it's NP-hard, and everyone's proving things were NP-hard around that time, so we discovered there were thousands of NP-hard problems. It could be, well, it's NP-hard, I don't know what to do, I'll just give up and design some heuristics. And to this day, people do things like that. But then people start realizing, well, even if I can't get the exact answer, it seems very hard to get the exact answer, and I might well work hard, and it might be, anything I come up with might end up running an exponential time, and I don't know if I can do any better. It turns out I can get close to the correct answer in polynomial time. And that was the first example of trade-off. Something that could be very bad, you don't know what it could be, maybe exponential, maybe not, versus something that was polynomial time with a guarantee. And yes, it wasn't quite exactly right, but it was close. And so historically, these were the first kinds of approximations people looked at, when the problem was just intrinsically very hard. Unlike some of the problems we've been looking at, where they're not really hard problems. I mean, linear space is bad, but it's not terrible. It's just bad in a large data context. These problems were just intractable. We just did not know how to solve them without being exponential time. And so that's when these things became very attractive, because you could get quick answers really quickly. Okay. So let's look at an example of this. So this is a problem called vertex cover. You may have heard of this problem before. If not, let me define it for you. I give you a graph. Again, as usual, there's vertices and edges. It's undirected. No loops, no usual stuff like that. What I want to find is a set of vertices that cover every edge. And what I mean by that, every edge should be adjacent to one of the vertices I pick. Okay? So think of these edges as kind of paths in some kind of dangerous cavern. And you want to put guards, right? So you want a guard to guard every one of these paths. And so a guard can see down a path, but it has to be there to see down it. So you want to put these guards in different places to make sure all paths get seen. And of course, guards are expensive, so you don't want to hire too many. Is the problem clear? Okay, let's look at that graph. What would be an example of a vertex cover there, or a good vertex cover? I want to find one of smaller sizes. So let's try to walk through this example. Okay, so any thoughts? Let me label them actually first, so it'll be easier to call out. Okay, so what do you think would be a good vertex cover? In other words, give me a set of vertices that together will cover all edges, and as far as you can tell is the smallest subset you can come up with. Yes?
2, 4, and 7.
2, 4, and 7. Okay, so let's mark off 2, 4, and 7. Okay, so there's 2, 4, and 7. No? Okay, wait. Who said no? So why did you say no? Tell me why you said no.
Because 2 covers both. Well, maybe it's not.
Is there an edge that is not covered?
Yes.
Which edge is not covered?
5 to 6.
5 to 6 and 3 to 6 are not covered. So this is not yet a vertex cover. Can we add something to it to make it a vertex cover?
6.
You can add 6. Is it now a vertex cover? So is it feasible? Does it cover all the edges at this point?
Yes.
Are you all satisfied about that? Okay, good. So at least it's feasible. So we know the answer is at most 4. right? We know that the answer will not be more than 4 because we have an answer of size 4. Can we do better?
164.
164. So let me change colors here. So I'm hearing 164 and 165. Okay, so let me just do one. So we have 6 and 4. Let's do 164. So I'm just going to put 25 is not covered. So 164 is not a good answer.
165.
165. Oops. Sorry. Wait. I'm going to do 165. You're all too fast for me. So 165. Is 165 working?
No.
It's not working. Okay. So far we still haven't got anything less than 4. Anyone else?
You need at least 4 vertices.
You need at least 4 vertices. Why?
3 cannot cover all it.
Why? The reason I'm asking why is because if you're ever going to be able to prove that your answer is decent, you have to be able to answer that question. So is there no matter what 3 I picked? Yes?
We have a room full of smart people and nobody's figured out one.
That is the rationale for NP-hardness. We have 3 decades worth of smart people trying to figure out answers to NPR problems and no one can figure out this. So it must be able to take exponential time. Therefore, please not equal to NP. No one has got a $1 million prize yet. That's not a proof. And this alleged group of smartful people, I include myself in this list, the alleged list, did not find what was it last time? Someone said last time there was it a min cut or something? We did not find the optimal solution to a question we had in class last time. 2 lectures ago. So don't overrate smartness here. Yes?
Can you relate it to an Euler path? Can you relate it to an Euler path?
To a what path?
An Euler path?
I don't know. Can you? I don't know. It's an interesting question. But for now, are we willing to be convinced that a room full of smart people can't find a set of size less than 4? Yes?
Well, I guess so. If you start with 6 and take away all the edges from that, it's a continuous path. From 7, 1, 2, 5, 4, 3. So for that path, there need to be at least 3 to cover that, I think.
Oh, interesting. So you said if you remove 6, what he said is if you remove 6, you get this path, and you need at least 3 things to cover that. Why do you need at least 3 things to cover that?
If there's 5 nodes,
Right.
you need 3 to cover them. Or no, wait.
You only need 2 to cover them.
Wait, you need 2. Wait.
No, the last, there's
4 to
6
3.
nodes. There's 6 nodes in the class.
Yeah, so this is the
Okay,
path.
yeah.
1, 2, 3, 4, 5, 6. And you said you need 3 things to cover it.
Yeah.
Why do you need 3 things to cover a path and then 6? I want you to hold that thought.
Okay.
I want all of you to hold that thought actually. I can give you a thought almost. You can hold the thought. So in the meantime, I also want you to hold the other thought you had. Take the 6 which has the highest degree. Why do you want to pick 6 as the highest degree?
Because I'm greedy.
You're greedy, and that's a good thing to do, to be greedy. In this class at least. So on that note, I want you all to pair up. Just for the purpose of discussion right now. Find a partner. Just find 2 people at a time. You're going to see why. Just 2 people at a time. I'll give you 2 seconds. Okay. Here are 2 strategies for solving the vertex cover problem. We'll call them greedy and whatevs. The greedy strategy is the one that Craig already mentioned. Pick a vertex. Here's the algorithm. Take your graph, pick a vertex of maximum degree, add it to your candidate set, delete the vertex and all its adjacent edges, repeat. Okay? This is an algorithm. It's a well-defined algorithm. It does something. That's the greedy strategy. The whatever strategy is pick an edge, whatever. delete it, add its endpoints to your set, and delete it, and then do it again. Okay? In each group, there are two of you. I want one of you to be greedy, and one of you to be whatever. You can take this graph or draw your own graph. I want you to spend 5 minutes playing with it tomorrow. Okay? So to draw a graph and pick one. I'll give you like 5 minutes. You want the graph? This graph is kind of easy, but if you want to draw it and make it more complicated, that's up to you.
So let's see. Pick vertex B and 20 G, which would be 6. S equals X. S equals X.
So you always start at 6, and then you take either 1, 2,
So, I mean, C, at least the adjacent there from G until is input at. So, you're like it so they're actually very similar. So they're basically what adds to the property fuzzy. Yeah, let's see. So pick an edge. I'm gonna label them as numbers, and then you're just gonna give me a number. Let's see.
You will add five into and delete those vertices and all the
Oh, sorry.
Questions? Hopefully you've all simulated or simulated the two strategies, the greedy and the lazy strategy, if you wish. Are there any questions so far? Yes.
I don't really understand. Because every single you're always going to get an even number of vertices.
Yeah.
Out of that.
Yeah.
You're going to have a cover of 6, or of 6 possible vertices.
Well, in this graph, you mean?
Yes.
Okay, and that's a bad thing because?
Well, we found a minimum cover of 3.
Well, we didn't. Ah, did I say either of these two would give you the exact answer?
No.
If either of these give the exact answer, I'd have $1 million and I won't have to teach this class. Because I have to solve P equal to NP. This is an NP-hard problem. I'm not promising you an exact answer. I'm saying they'll do something. And they're all going to be bad. But they're going to be something, yes.
So in the 1Ms, why do we pick both vertices instead of just saying pick an edge and then randomly choose one of the vertices?
Yeah.
Why do we pick both?
That's a good question. First of all, we don't even know why we do this algorithm in the first place. Are they at least correct? They're all correct, right? They give you the correct answer, yes?
So give an answer.
They give an answer. Very careful. Okay, good. I notice everyone is harassing me about what ifs. No one's asking about the greedy algorithm. Does anyone have any questions about the greedy algorithm?
In finding the vertex with the maximum degree itself going to take time?
Sure. Well, let's say we're not, as long as we're polynomial time, we're not quite yet worried about time. We're trying to understand how good the answers are. We should be worried, but for now, let's pretend we don't worry about it. So it takes a bit of time to find it, but it's not that bad, right? So no questions about greedy. It's all about the other one. Yeah.
Could you give an example where the greedy performs worse than the other?
Can I? What do you think? Can I give an example?
I think you could.
I'm not incredibly sure about this, but I think if you had a center point and had kind of a spoked wheel pattern,
Yeah.
that might make it so when you remove the center, the rest of it becomes linear.
And then?
Which and this is just by intuition, think might be worse than starting to pick edges along the side.
What do you think? What do you think? I'm like, whatever. If someone else gets the answer, I don't do it. So, so a wheel with the spokes around it, but they're connected up. Otherwise, it wouldn't make sense. Yeah. So you think of a cycle, and you put one thing in the middle, and you hook it up to everything. So his claim is that you'll pick that middle one because you're greedy, and then you have to somehow take half of what's left, essentially, because it's a cycle now. Whereas the other one, will do what?
I have no idea. I said it was an intuition.
Any other thoughts on the two algorithms? Apart from the fact that something and they give some answer? Yes.
I I'm not sure if we can find a better performance on what ifs as compared to greedy.
You think that greedy is going to do better than what ifs? You're
Yes.
just not convinced. You just think that it's like.
I mean, whatever examples I would come up with.
Yeah.
Basically.
Fair enough. Okay. Let us now try to analyze these algorithms, which is the crux of course doing approximations. You don't just want to come up with something. You want to be able to prove that it does something reasonable. Let's start with the greedy algorithm. Because greedy strategies, I should say that in approximation algorithms, a greedy strategy is often the first and a very reasonable strategy to take. Okay? Because if you don't know what else to do about the problem, try a greedy strategy. More often than not, you'll get something reasonable. Whether it's the best or not depends on your problem. And in fact, there's a large class of problems for which you can guarantee it's the best thing to do. Which is, we'll talk about that later on in the course. But even at any rate, it's always a good first step. It's like when you're doing recurrence, right? There's always you find some guess and try, it's always a good way to start. Greedy is always a good way to start. So let's try to analyze this greedy algorithm. So I'm going to introduce some notation. Don't get distracted by the pigeons, we'll get to them in a second. So let's say GI, so we were removing vertices from the graph. So let's say GI is the graph after you removed I vertices, okay? Let's say DI is the max degree of a node before you removed it, so the GI minus 1. So D1 is the max degree vertex in the original graph, G0. Okay. And let's say cardinality of G will be the number of edges, because that's what we really care about. Normally this would be ambiguous, but let's just say we only care about the number of edges. Okay. And let's say opt is the size of the optimal vertex cover. And this is what we're trying to compare against. So there's always a game. We always, okay, let's assume an optimal solution. We want to compare against it, right? Because we want to see our algorithm does reasonably well. The first claim to make in all of this is to say that there's always a vertex that has pretty large degree with respect to opt. Okay? Now you might say, well, I could have a cycle and every vertex has degree 2. That's not true. I didn't say it has large degree. I just said it has a large degree in relationship to the optimal solution. And that's the point. What do I mean by that? So let's imagine, and this is one thing we'll do all the time in approximations, imagine the vertices of the optimal solution. We don't have it, we don't know what it is, but let's just imagine them. There's this optimal solution that someone gave us, it's optimal, right? What do we know about the vertices of this optimal solution? Well, it's a solution, first of all. Forget optimality, it's a solution. Which means that it covers all the edges. Which means if you sum up the degrees of those vertices, they will be more than the total number of edges in the graph. Because at the very least they cover all the edges and they might duplicate coverage. Right? So the total degree has to be more than the number of edges in the graph. You agree? Okay. Then apply the pigeonhole principle. If the sum of all the degrees is more than the number of edges in the graph, there must be some vertex whose degree is greater than equal to the number of edges divided by the optimal solution. On average, right? It's the same trick we've been applying over and over again. If the sum of things is something, then at least one of them must be at least more than that divided by them. So far, I'm not sure this is where I'm going with this, and I'm not going anywhere yet. All I'm saying is that I have some vertex that has a reasonably large degree. Remember what our algorithm is doing. It's finding the vertex of maximum degree, right? So for sure, the degree of the vertex that my algorithm finds is going to be more than this. It might be this, but it might be more than this. Because I'm guaranteed to have something that's at least reasonably big. Okay? Notice this could still be 2, like in our cycle case. I'm just saying in relationship to opt as well. Is this claim clear? Again, you may not see where we're going with this, but at least the statement, the claim, the proof, hopefully that's clear as well. Yeah? Okay. What next? Now we can start actually understanding what the algorithm is doing. What is the algorithm doing? As I said, because we know that there's some vertex that has degree at least g over opt, we know that what we pick, the d1, the vertex of max degree, has to have degree more than g over opt. Right? So g0 over opt. Similarly, once you go to the next one, d2, by the same reasoning, we'll have vertex greater than g2, g1 over opt, and so on. Okay? So if you sum up all these degrees, the degrees of all these vertices, by this inequality, it's greater than equal to the sum here. Which of course is greater than equal to that because the graphs are getting smaller and smaller and smaller. I'm replacing a term inside the summation by a smaller term. I'm replacing this term by that term. So obviously the number is getting smaller. But this is merely that. Okay? Again, some algebra, again, maybe not quite sure where we're going, but just hopefully you can follow the steps of algebra. In other words, I have this inequality up here, I now sum up these degrees. Why? Because I feel like it, and then this gives me this bound here. But what is G-opt? G-opt is what you get, what the graph you get after you've done opt number of deletions. I don't know what opt is. I don't care. My algorithm is running after some number of iterations. I don't know how many. Because I don't know opt. I know this property, that di is more than G-opt. Again, I don't know where it is. And in particular, we know what G-opt is exactly. It's equal to the number of edges in the graph minus all the degrees you subtracted out. Because once you take a vertex and subtract its degree, you don't count its degree anymore, it's gone. So it's exactly that quantity there. The degrees are with respect to the graph you're in right now, they're not with respect to the original group. Okay? But that's the same as the left hand side. So we're saying that di, sigma di is greater than or equal to G minus sigma di. Or sigma di is greater than or equal to G over 2. You get a bit of algebra trickery here. What this is basically saying is that we are making lots of progress. Because the intuition is the following. We have a vertex that's of high degree in relation to opt. So if we pick it, we're going to remove lots of edges. Why are we happy about removing lots of edges? Because every time we pick one vertex, we're adding one count to our cover. If we can remove lots of edges each time, and that's the intuition for the greedy algorithm, we will stop very quickly with a small cover that has covered all the edges, right? That's the idea of the greedy algorithm. We want to get as much as we can. And what they're saying, yes, in fact, that happens. If you pick a vertex of reasonable degree, after a certain number of rounds, off number of rounds, we have in fact reduced the number of edges. In particular, the number of stuff we removed is more than G over 2. We have reduced the graph by half. The number of edges in the graph after opt rounds. We don't know what opt is. We're just running our algorithm. But at some point we know, in the middle of the process, our graph size is going to be down by a factor of 2. Is that a good thing? Can you see ahead to what's going to happen next? If I just said I can do something and reduce my graph by a factor of 2, I can do it again and reduce my graph by a factor of 2. And then do it again and reduce my graph by a factor of 2. How many of these agains will I need? Sorry? Something like log of the size of the graph, right? The graph has n squared edges, log of n squared. So like a log n rounds. In each round of opt pulls, we reduce the graph by a factor of 2. After log n rounds, our graph will be empty. So this is what's called making progress. We're making good progress. So since we've proven this lemma about making good progress, we know we can complete the argument and say this. That if we pick up opt vertices, the graph halves in size. After log g such batches of picking opt vertices, we're done. How many vertices have we picked? Opt times log n. But that's exactly what we want to show. We want to show that's the relationship between the set we pick and the optimal size. In other words, we have now proven that our algorithm has an approximation ratio, which is opt, s divided by opt, which is O of log n. We have given a log n relative approximation algorithm for vertex cover with the greedy algorithm.
No question. Question.
Yes.
Could you go to previous page? Yeah. So size of G of, should it be less than size of G minus the degrees?
No, because remember the degrees are being measured in the graph you currently are in. So that when the previous vertex pulled off its degree, you don't count that for you now.
Okay.
So there's no double counting going on. That's the trick. That's why the degree is defined with respect to the graph that you're currently in right now. So this will take a bit of reading, I suspect. You might have to go back home and sort of read through this argument again. But for now, what I want you to understand is the following intuition, which is being translated into the mathematical argument here. We want to show that at every step we remove a reasonable number of edges in the graph. Because if we can do that, then we know that after a certain number of steps we stop. And those number of steps will be few. We are able to show that a single vertex we pick has a large degree with respect to opt. And therefore, when we pull it out, we make progress. And in particular, we make enough progress that we can half the size of the graph. And then we know that at that point, if we do that log n more batches of that will be done. Yes?
So does the value of opt not actually matter then?
It doesn't. That's the point. It doesn't matter.
So
We're just running it till it stops, and we know when it stops, it has to run for at most that many steps. That's the key here. Without knowing opt, the algorithm is just running. You saw the algorithm. You ran it. Really. We are trying to retro-analyze what the algorithm is doing with respect to opt. And this is the essence of all approximations. You have the algorithm. Of course, you have to design the algorithm keeping these things in mind. It's a back and forth. But the algorithm itself tends to be oblivious. It's usually oblivious because you don't know what the answer is. But what it does for you is that by knowing, guessing, okay, if opt is like this, this is what will happen, you can actually analyze it. So it's a very kind of backwards way of thinking about algorithm analysis. And that's what makes it hard. Yeah.
I'm sorry, when you say the size of G halves, how do you define the size of the graph?
The size of the graph is the number of edges in the graph. Right?
Okay, so.
And what we said here was that, if you look at the reasoning here, we first showed that the sum of di through a chain of inequalities is greater than or equal to the size degree at opt. That was one inequality. The second equality is just by definition of G opt, it's the graph you get after you remove the first d vertices, the first opt vertices, and therefore the number of edges is exactly that, because each vertex removes di edges from the graph. Putting those two that equality together with that inequality, you get di is greater than or equal to G minus di. Then flipping that around, you get di is greater than or equal to G over 2. So there's a step of algebra right there, where this goes that side, becomes a factor of 2, and then goes down to becomes G. Again, you might have to read through it a bit more carefully to see how the algebra works, but that's the idea.
That's basically saying that the graph is composed of two set of vertex and a set of edges, and the size of the graph, which is equal to the number of.
I'm defining, yes, I'm looking at only the number of edges in the graph, that is correct. I'm using the word size here to refer to the number of edges. I don't care about the number of vertices. Because my goal in vertex cover is to cover all the edges. So that's what I'm trying to do. Okay. So this gives us a log n approximation to the vertex cover problem using the greedy strategy, which is nice. We have a formal guarantee now on what it can do for us. Yes?
If the algorithm didn't care about the vertices themselves, just the number of vertices that would make the minimum or make the vertex cover, then
Just the number you mean? Or just the set?
just the number.
Just the number, yeah.
So then would you just simply keep pulling up vertices until G shrinks by half, and then that would be your answer?
You could do that and say log n times this number is my guess. You can't say that's your number because it could be much less than the number. And ultimately, if I give you a set of vertices, okay, just multiply this number by log n, you're done. I'm going to say I don't believe you. The advantage with this algorithm is that it gives you the actual set. You can check, okay, this is in fact a set. This is in fact a vertex cover. It's a proof in some cases. But it also is a proof of being good. But yes, there are a lot of problems for which if you just want the number and not the actual set, you could do better. And one way to do this is make a guess based on this. But the guess you make will be you might be off balance. Okay, so that's so much for the greedy strategy. Let us now try to analyze the what-if strategy in the same way and see if we get something from it. Here's the observation I want to make, which is very important. The set of edges you pick one by one, if you imagine, okay, I pick this edge, write it down somewhere, pick this edge, you delete it from the graph, let's keep track of those edges you pick. It forms a matching. Remember a matching? A matching is a graph in which you have no two edges that are joined together, they're all separate. Right? So this is a matching. Right? This is what a matching is. A set of collection of edges that all have vertices of degree 1, and they have no two edges are adjacent to the same vertex. The set of edges you get in this graph as you pull them out form a matching. Why is that? Well, I take an edge, I pull it out. But then I also pull out all the edges adjacent to it by definition, right? I take U and V and I delete all the neighborhood. The next edge I pick cannot be incident on U and V, it's gone. So the next edge I pick is different, the next edge I pick is different, and they form a matching. that clear? This is very important. Okay, let's list out all these edges. If I have k edges that I picked, what is the size of my vertex cover going to be? As you pointed out, it's going to be even. It's going to be 2 times k. Right? If I pick k edges, I'm going to pick each of their endpoints. I want to have 2k vertices in my set. Okay? All right. So far, so good. We haven't done anything. Now the key question is, what would the optimal algorithm do? Now these are edges in your graph. They're not, I haven't manufactured them. They're real edges in your graph. They have to be covered by opt. How much must the optimal algorithm pay to cover these edges? Think of the best possible algorithm you could imagine. How many vertices would you need to pick?
At least half of them.
Why?
If all of those edges are covered, then that means that one of those 2 vertices had to be covered.
Because there's no way to leverage
Yeah.
one vertex to cover more than one of these edges.
Yeah.
Because they're not connected to each other. If I pick this, I cover this, everything else still stays the same. The optimal solution on this set of vertices must be at least k. There's no way around it. You have to pay k to this. Okay? What does this mean? Well, S is 2k. Opt is greater than or equal to k. So then opt is greater than or equal to S over 2. We have a 2 approximation. So in other words, we said that our solution is of size 2k. We said the optimal solution is of size at least k. You therefore show that opt is greater than or equal to S over 2, because S was 2k. And therefore S is less than 2 opt. S over opt is less than 2. The what else algorithm is way better than the greedy algorithm. Much better. As n gets larger, the greedy algorithm ratio can get huge in the worst case. Or might, we don't know. That's all we can analyze. Whereas the what else is always within a factor. So do you see what's going on here? In the case of the greedy algorithm, we were trying to understand progress. We're saying, okay, how much progress can you make at a step? Basically, every greedy algorithm you ever will encounter works that way. It says, I make certain amount of progress at a step, how many more steps do I make? You do gradient descent, you do stochastic gradient, anything you do which is basically greedy, you measure its progress by saying how much work can you do in one step, and then how many steps is needed to get there. And that's how we did. Here we're doing something a little bit different. We're saying the algorithm is finding some blocks, some kind of structure in the graph. And that structure in the graph is hard for the optimal solution. And we're not too bad with respect to that. It's what's called a lower bound. And that's how we reason about what the algorithms do. So I want to spell this out in a bit more detail. Right? So we're saying that let's say we want to minimize something. In this vertex cover problem, we want to minimize. All approximation algorithms for these problems will work in 2 steps. We come up with some kind of property of the graph that may be constructed from the algorithm or otherwise. And we show the algorithm is less than or equal to some constant times that property, somehow. In this case, the property was k, the size of the matching, and the algorithm was less than or equal to 2 times k. Then we show the optimal solution is more than that property. Optimal is more than k. It's a lower bound of some kind. And then you put these 2 inequalities together, you get the bound you want. So schematically, if you think of, I'm looking at the cost of my solutions, which is going down. The optimal problem, which is somewhere here. Let's say this is optimal. Right? I don't know what the optimal solution is. It's very hard to reason about it. It's an endlessly hard problem. Who knows what to do? But I am able to find a little bit more quickly some kind of lower bound on the optimal solution. And I can reason, my algorithm is somewhere here. I can reason about how good my algorithm is with respect to the lower bound. Clearly, if I can reason about how good my algorithm is with respect to lower bound, it can't be any worse with respect to optimal. And that's how we prove approximation models. And that's why I was asking, you were saying there's some reason why I can't do better than 3. You have to reason in this form by saying, oh look, I have now produced 3 edges that are a matching. You cannot do better than 3 on those. So if I get a 4, I'm 4/3 approximation. In that case, in that graph, you could probably get a matching of size. So let's actually go back to the graph for a second. I wanted to go back to the graph and see. This is 7 vertices, so it's not quite going to work. You're not going to be able to get a matching of size 4. So you can't easily prove this, but there's at least a matching of size 3. So the optimal solution is at least 3.
Should be more than 3.
Maybe, but
Yeah.
and I'm not promising more than that. I'm not saying it has to be exactly that. It's more than that.
Yeah.
So if I get a solution of size 6, which I get from the what ifs answer, it's within a factor of 2.
Yeah.
And so I'm always within a factor of 2.
So greedy or what else both are not like guaranteed to give an optimal solution.
No.
Both will give an approximate or.
And the question is, what can they give? They give a provable approximation and they give different provable approximations. And that's the crux. And all the work in approximation algorithms, all the work you do is in finding this. Find this lower bound. And we'll see more examples. This is not an easy thing to do. It takes a while to get used to. I wouldn't even call myself anywhere close to being an expert on this. There are people who are. But it's just a different way of thinking about algorithm design. You think kind of backwards.
So if we sort of combine them and find the biggest matching, does that help us at all?
Find the biggest matching, in fact it does. If you take a graph and find the best matching in the graph, that is the lower bound on the size of the vertex cover. That gives you an answer. This is, for bipartite graphs, these things are the same thing. This is called Koenig's theorem. If you take a bipartite graph and you find a maximum matching, you can pull out a vertex cover from it immediately, which is optimal. So for bipartite graphs, you can find the optimal vertex cover because of the relationship to maximum matchings. In a general graph, the maximum matching is not exactly the same, gives you the same vertex cover, but it's within factor. And the reason why this all happens is because of linear programming, and we'll see that in a few lectures. There's a deeper magic going on which makes all of this work, especially for the vertex cover. But you don't quite see it yet because you don't have the right language yet to talk about. Yeah?
So if you were to run the whatevs algorithm more than once, and
You might get different answers each time.
And the first time you got like 10 edges,
Yeah.
the second time you got 8 edges,
Yeah.
then you know that your 8 edges is a better answer.
But you also
But you
know
know
that
that you're closer, you know, like your lower bound is 10.
it's
but
5
you got
actually. The
16.
other one is 5. Oh, 10 edges, sorry, 10 edges. Yeah.
Yeah, so we have 10 edges in one solution, 8 edges in another. So the 8 edge one, you have 16 vertices in that one.
Yeah.
But you know that the optimal is at least k.
Yeah, that's not
There's
going to
at
happen.
least 10.
You're not going to find 8 edges in the second, you found 10 edges in the first. Because actually what you're finding with that algorithm is a maximal matching. So it could happen, but it's unlikely. Yeah. So, okay, maybe I got distracted. What was your question again? Sorry.
So if you got 2 different sets of pairings,
Yeah.
then you could have a different bound on your lower bound, then you know you could do better than 2. You could say I have an accuracy.
You won't, but you can't guarantee that. It may be for a particular graph in a particular run you do better. But in the worst case over all graphs over any run,
Right.
you can't guarantee better. That's the point. It's a worst case guarantee. Questions? Yes.
So, as far as we're trying to learn to create these algorithms, greedy is a method for trying something random.
Trying something.
Trying something that has a good chance of working, right?
Yeah, not random,
So
because
how
random
do
means
you-
something different.
How do you follow, what method do you follow to come to an algorithm like this one? Do you just literally try things?
That's true for everything we do. You literally try stuff. Greedy is one thing to try. These things actually can, there's a general hammer you can apply for a lot of these problems via linear programming, and I'll talk about that in a bit. There's a sort of a generic technique. Express your language. If you can do that, then turn the crank, and out pops an approximation. You still have to prove that it gives you the right answer, but it'll give you something, so at least a candidate solution. And in fact, that's how you get this maximum matching work. That's one way of thinking about it. Another crank is, if your problem belongs to a certain family, and I apply a greedy algorithm, I am guaranteed to get 0.637 approximation to the correct answer. This is what is. So there's a whole class of problems that if they have a certain structure of the problem which you can inspect from the problem definition, then you know for sure that a greedy strategy will give you the best possible strategy. So there's lots of things like that where you can now you have clues as to how to attack the problem. If all else fails, of course, you need to invent a new method. But the hope is that for many things you can start off with that, and that's a reasonable answer. Yeah?
Is Vertex ever NP-complete?
Yes.
So does that mean that the other NP-complete problems are going to have, or could they be shown to have similar bounds?
Aha! That's a very good question. No. The problem is that the reductions that show that problems are NP-complete are reductions that merely show that could be problem. It either is correct or not. So the way to make vertex cover into an NP-complete problem is to say there's an extra parameter k, and you want to know, is the vertex cover less than or equal to k or not? It's a decision problem, there's a yes-no answer, and then you can construct a chain of reductions. The problem is that the chain of reductions does not preserve approximation quality. For example, vertex cover, you just defined. If I take the complement graph of vertex cover, I get what is called independent set. That if I take a graph, compute the vertex cover, and take its complement, all of those vertices are not connected to each other. You can see why, because if you took two vertices not in the vertex cover, they're connected, that edge is not covered. So if you take the complement of the vertex cover, it's an independent set. The smallest vertex cover gives you the largest independent set. So independent set is NP-complete as well. But if I now say, oh, I have an approximation out of the vertex cover, can I get one for independent set? You can't, because the sizes are different. A 2 approximation for a small quantity is not a 2 approximation for a large quantity. And in fact, independent set is way harder to approximate. Much harder. So you need a special kind of reduction called an L reduction. And that leads you to a taxonomy of NP hardness, but of approximation hardness within NP. And we'll talk a little bit about that later. So there's a whole richer, think of it like NP hardness as being a crude lens, hard, easy. You look really close to a microscope and now you see, well, kind of easy, really bad, oh this is terrible, and inside the NP hardness range. And that's what approximations gives you as a new lens. And we'll see that lens coming. Okay? Vertex cover would be considered one of the reasonably well-behaved people in this family. Not the best, not the ideal model student, but a reasonably well-behaved. We'll see vertex cover's wilder older brother in a second. Set cover. The set cover problem is a generalization of vertex cover in the following sense. My input to my problem is not a graph, it's a collection of sets from the universe. Okay, so I just have a collection of subsets. Let's say the universe is 1 through 100, and I give you a bunch of subsets of 1 through 100. And my goal is to find a sub-collection of these sets. So just pick off a few of these sets that actually together give me the entire space. So I should have said this slightly differently. This is not quite right what I said, because that may not actually be true. Let me say it slightly differently. It's really... In other words, these sets all overlap in strange ways. So let me try and draw an example here. Let me put a new page in. I don't know how to insert a page. Can I insert a page? New page. Okay. So let me take so let's say my set, my universe is equal to 1 to, 20. Okay. So let's say S1 is equal to 1 to 15. S2 is equal to 17, 19, 20. S3 equals 16, 18. S4 equals to even numbers less than 20. Okay? This is my input. I want to find a sub-collection of sets that cover what these numbers cover. And you should be able to see that I can just pick these 3 sets. Because S1 union S2 union S3 is in fact equal to S1 union S2 union S3 union S4. Right? So my solution to the set cover problem, so the solution here would be the sets 1, 2, 3. Okay? And I want to find a smallest such collection. Yes?
So we just said last, the size of set should be as.
The size of the collection. So
Yeah.
I want this set is equal to 3 and minimize this.
So we can use S1, S2, S4 as well.
Yes, that's correct. So it's cover because if you then it's easy to see that if you solve this set cover problem, you solve the vertex cover problem. So now you're picking these sets which are basically vertices that cover all the edges. And in particular, because vertex cover reduces set cover, and it reduces in this kind of very simple way, it does not do anything fancy, the greedy algorithm works. In other words, if you take the greedy strategy, take a set that covers the most number of elements, pull it out. Take the next set that covers the most number of elements, pull it out. By the same analysis as before, you get this log n approximation. What's interesting though is that the what-if strategy doesn't work. The approximation you get is an F approximation, where F is the maximum size of a set. For vertex cover, all sets of size 2. Your edges of size 2, so things work. Here it doesn't work. So for set cover, in fact, the greedy is better. You get a log n approximation, assuming that your sets, and you can't do any better. You can prove that to get a better than log n approximation for set cover is itself NP-hard. So vertex cover, like I said, was the reasonably well-behaved child of the family. Get a 2 approximation. 2 is not great, but it's still a constant. Set cover, the wilder older brother, has a log n approximation, which gets really bad. And you can't do any better. That's the point. For vertex cover, we don't know. You might be able to do better than 2, we have no clue. We know you can't do better than, I think, 1.01 or something. But that's all we know about it. It seems unlikely that we can do better than 2. People have been thinking of this problem for 30 years now, and we don't know how to do better than 2. So it seems very unlikely. So again, because set cover is a very close variant of vertex cover, and it's not obvious, you have to actually prove this, but the same proof technique works. You can't just say, oh, vertex cover to set cover, therefore it works. You have to prove it. But the same algorithm idea, take the greedy strategy and apply it, with the same analysis, will give you the log n approximation. Just by using the same reasoning. Look at the optimal solution size, look at how much progress you make at every step. There's one set that must be reasonably large. Okay. And again, in both cases, with vertex cover and set cover, there's this whole business of you try to understand some kind of lower bound on what the problem is trying to solve, on this problem, and then try to reason about what you have. And so, I'm not going to talk about traveling salesmen just yet, but I do want to say one thing, which is this. What we're going to see, and we'll see this very soon, oops, okay, is that, as I said, we have the whole bag of, NP-hard problems. And they're all hard in the same way. To solve them exactly, we don't know any better solution right now than to do something that takes exponential time. Maybe you can do better, we don't know. But when you start asking which problems you can approximate, they start separating out into different categories of problems. Some of which are easy to approximate, some of which are harder, and some of which are harder. So I drew these 4 lines somewhat deliberately. Vertex cover is somewhere here. So this direction is easier. Set cover is somewhere here. Independent set, complement of vertex cover is somewhere up here. And we'll see problems in this category shortly, where you can get arbitrarily good approximations. So it's not 2, it's not 1.5. You want 10% error, I'll give you. You want 5% error, I'll give it to you. But you got to tell me the error first. I can design a strategy of it. Okay? And these are the kinds of things we like. Because that means you can get as close to optimal solution as you want. Actually, the running time will go up. But we'll see how that works. So this is what I mean by the lens expanding. You see this lens expanding of what you can do with these problems, and we'll see more examples of these as we go along. Okay? All right, a few minutes left. Any questions for today? About vertex cover or set cover? Yes?
So going from the set cover to vertex cover, was that kind of what we were talking about, the reduction, not?
That was a good reduction. That actually does. because the sizes more or less remain the same. So that's why we could use the same algorithm to work. But you have to look at it on a case-by-case basis. You can't generically assume it's going to work. Okay? See you all on Thursday. Don't forget, you have to start thinking about your projects and your groups, and please check. For some reason in Canvas, even though I can pretend to be a student who doesn't let me get the right interface, so let me know if you have trouble forming your project groups. Okay. Yeah.